Two classic problems. QuickSort sorts the entire array. QuickSelect finds the element that would sit at index k if the array were sorted. Both use the same idea, Lamuto partition with the last element as pivot, then they recurse differently. We partition using the last element as pivot. Index I is the boundary, everything to the left of I is less than or equal to the pivot. Index j scans. When ARR, j, is less than or equal to the pivot, we swap into I and grow the left block. Finally, we place the pivot at I. At j we have 5. It is greater than the pivot, so we only advance j. At j we have 2. It is less than or equal to the pivot, so we swap with the value at I, which is 5, and advance I. At j we have 7. It is greater than the pivot, so we only advance j. At j we have 1. It is less than or equal to the pivot, so we swap with the value at I, which is 5, and advance I. At j we have 9. It is greater than the pivot, so we only advance j. At j we have 3. It is less than or equal to the pivot, so we swap with the value at I, which is 7, and advance I. At j we have 6. It is greater than the pivot, so we only advance j. Scan done. Swap pivot 4 into position I, partition returns index I. The pivot will not move again. QuickSort recurses on both sides. QuickSelect recurses on only the side that contains k. After partition, the pivot is fixed. QuickSort recursively sorts the left segment and the right segment until every subarray has 0 or 1 element. We want the second largest element. In sorted order, that is index k equals n-2, here k equals 4. After each partition, if the pivot index equals k, we stop. Otherwise we recurse only on the side that still contains index k. Swap within the left block. Swap within the left block. Swap within the left block. Skip, j moves on. Skip, j moves on. Place the pivot. Compare index I with k. Pivot landed at index 3, but k is 4. Since k is greater than the pivot index, we recurse only on the right part, indices 4 through 5. We partition again inside the active range. The pivot is still the last element of that range. Skip, j moves on. Place the pivot. Compare index I with k. The pivot index equals k, so we return ARR, k, which is 5, the second largest. If k is less than the pivot index, recurse only on the left. If k is greater than the pivot index, recurse only on the right. Average time drops to linear in n because we discard roughly half the work on a good split. N is the length of the array. QuickSort averages n log n time when partitions are balanced, but n squared in the worst case when the pivot is always extreme. QuickSelect averages linear time because each step recurses into only 1/2, but worst case is still n squared with bad splits. Space is dominated by the recursion stack, logarithmic depth on average, linear in the worst case. Pseudocode for Lamuto partition and quicksort. Partition places the pivot, then quicksort recurses on both sides. Initialize pivot value and I at low. Scan J across the range. If ARR, J, is less than or equal to the pivot, swap into the prefix and advance I. Swap the pivot into its final index for this call. Return the pivot index. Quicksort, sort the subarray from low to high. Recurse only when the segment has more than one element. Partition and get the pivot index pi. Recurse on the left subarray. Recurse on the right subarray. Pseudocode for QuickSelect. After each partition, recurse only into the side that still contains index k. Base case, only one index in the range. Partition the current range. If k equals the pivot index, return that element. If k is less than the pivot index, search only the left part. Otherwise search only the right part.